Hey, what's going on guys, Tanmay here for Simple Snippets and welcome back to another video tutorial on Heap Data Structure, and let's continue with our implementation part of the Min Heap Data Structure that we've been doing in the past few videos in this DSA course. In today's video, we're going to understand the delete key operation in detail. We're going to take a look at the pseudocode, we will dry run it step by step, we will see the working with the help of diagram, and at the end of this video we will write a C++ code, that is, we will completely implement the delete key function and complete the practical side. Now before we proceed, a quick disclaimer. If you haven't watched the previous video wherein we implemented the extract, min and heapify operations, then this video is going to be very difficult to understand because basically delete key is completely dependent on extract, min and heapify operations. So please pause this video and go back to the previous video in this DSA course and watch that video first. If you have already seen that, if you're following this DSA course, then this video is going to be a piece of cake for you. But for those who haven't watched that, please watch that. Without that, this video is very difficult. Okay, so now that the disclaimer is done, let's start off with understanding the delete key operation. Now delete key, as the name suggests, is when we want to delete a particular value in the heap data structure. Now we are implementing the heap using array, correct? And this is a min heap. So the minimum value, that is the node with the minimum value, will always be at the root level, right? So this is a min heap. And you can see the minimum value is 6, which is there at the root level. And for every node, its parent is smaller than its own value and all its children are larger. So if you see this node, its parent is 6, 6 is smaller than 33, and all the children of 33 are larger than its own value, correct? So that's the basic principle and definition of min heap. Now when you want to delete a particular value in this heap data structure, we take an indirect approach. What do I mean by that? So let's say you want to delete the value 40, which is at index position 3. You can see at index position 3 over here, and diagrammatically it is placed at this location. You want to delete this value. So the approach that we're going to do is we're going to make this 40 a minimum value. So we're going to replace 40 with a very small integer value. Let's assume -1 in this case for now, okay, just for representation purpose. So when you make this value as -1, now this is basically violating the min heap property, right? Because for this node, the parent node is larger and that is not possible in a min heap. So for a particular node, its parent node always has to be smaller. So that's why now we will have to swap this -1 and bring it at this location. So then we will do that. So 33 comes over here and -1 comes over here. Is it still a min heap? No. Still, -1 is smaller than 6. 6 is the parent of -1. So we still need to swap one more time. So 6 comes over here and -1 comes over here. So one part of the delete key operation is done. So on the left hand side you can see the pseudocode, but right now I'm just trying to explain with the help of diagram. So once you get this value at this location, that is the top location, which is the root node, now you can use extract min function and extract the root node. So remember, extract min basically removes off the root node. So you'll return this outside and then this node will be completely erased off. And then in the extract min, remember we had heapify, right? So heapify will be called and the entire heap will be recreated from all the remaining values. And do note that we have successfully deleted the number 40. So in the heap now, you can see we don't have the number 40. So that's how delete key operation works in an indirect way. There are two-step approach that we take. First, we decrease the value to a very small value that you want to delete. So let me just quickly resume back to the original heap. So coming back, as I said, since we wanted to delete 40, we replaced 40 with a negative value or a very small value. Then we took this number and brought it to the root level by using swapping. And then we called extract min and removed off the root node. So basically we deleted this value and then we have to recreate the heap because we called extract min, so we'll have to heapify from the top, right? So this is how the delete key operation works with the help of diagram. But now let's try to step by step dry run the pseudocode, okay? Okay, so on the left hand side, this is the pseudocode for delete key and we pass an argument which is basically the index position. So I is nothing but the index position of the value that we want to delete. Remember, we are playing with arrays and to access a particular value in the array, we require the index position. So let's assume that the index position that we want to pass is 3 and we want to delete 40. Okay, we'll take the same example. So I is gonna be 3. Let's keep a track of all these values. Let's write I equals to 3 over here. Alright. So step 1, as I said, we have to decrease the value. So we create a separate function called decrease key. Okay. We pass the index position I. So 3 is passed as it is. And this int underscore min is a predefined standard variable in C++, which is basically the most minimum value an integer data type can hold. I'll put the value of that int min variable on the screen. So it is a standard fixed value. You can create your own minimum value also. If you know that the numbers are going to be positive numbers, you can create a inbuilt variable or you can create a global variable with a negative value. But we'll go ahead with int min. Okay. And let's assume right now that the int min is -1 for simplicity purpose, although it is not. Okay. So what is this decrease key function? So decrease key function is again a separate function that we'll have to write. And as the name suggests, it will reduce the number at this index position 3 to a very negative value. And then it will also bring it to the top, right? So let's see the decrease key pseudocode. So this is that second function. So from delete key, we are giving a call to decrease key. Okay. So now let's start off with dry running this decrease key. So int I that we passed is 3. So I over here is also again, let me write I equals to 3. And this int min is the int new val. So new val, let's assume it is -1. Okay, we are just assuming, remember this int min is not -1, it is a standard minimum negative value, but for simplicity purpose we are taking -1. Okay, so inside we say h array of I equals to this new value. So I is 3, right? So h array of 3 is going to be this index position and we are assigning this new val over here. So let's make those changes in the array as well as over here as well. So we say -1 over here and -1 over here as well. Okay. So first step done. Let's proceed with the second step. In second step, we are saying if I is not equal to 0, I is right now 3. So it is not equal to 0, which means this is true. There is one more condition and h array of parent of I is greater than h array of I. So remember, parent was another function which we wrote, which basically gave us the parent of a particular index position. So over here, when you pass parent of I, you're passing I is 3. So parent of 3. So when you pass index position 3, you'll get index position 1 as the return value from this function, because you can see the parent formula and you can see the function over here on the screen. We've already discussed this in previous tutorial, so I'm not, taking up that again. But you'll get 1 as the result of parent of I. And then h array of parent of I, is it greater than h array of I? H array of I is nothing but 3. H array of 1, what is h array of 1? It is 33. Correct? H array of 1 is 33. Is 33 greater than h array of 3? We just did -1 at h array of 3. So is 33 greater than -1? Yes. So both these conditions are true. In that case, what we will do? We will do a swap. We will say swap these two values. So we will swap -1 and we will put it at 33's position and 33 will come over here. Okay. So let's do that. Okay. So 33 comes over here and -1 comes over here. In the array also, let's do the swapping. Okay. So the swapping is done. The next step says I equals to parent of I. So I is 3. When you say parent of 3, you'll get 1. Remember? So now 1 is stored in I. So I now becomes 1. Let's write I over here. I becomes 1 inside this decrease key function. So again, you'll come at the start of the while loop. You'll check, is I not equal to 0? Yes, this is true. And again, you're now going to check h array of parent of I. So this time parent of I is 1, right? So you're passing 1 in parent function. When you pass 1 in parent function, you'll get 0 because 0 is the parent of 1. So basically what you're saying is h array of 0, is it greater than h array of I? I is 1. So h array of 1. What is h array of 0? We have 6. Is 6 greater than h array of 1? What is h array of 1? It is -1 because we brought -1 over here. Is 6 greater than -1? Yes. So both these conditions again became true. So again we will do a swap of these two values. So -1 and 6 will be swapped now. So 6 comes over here and minus 1 comes over here. In the array also we'll do the swapping. Minus 1 comes over here and 6 comes over here. Right? So this step done, swapping is done. Swapping is again our own user defined function. We've already done that in previous tutorials. So you'll see in the code also. It's a simple swapping technique. Okay. So moving on to the next step, we say I equals to parent of I. So I was 1. So when you say parent of 1, you'll basically get 0 because parent of 1 is 0. So now I will become 0. Correct? So you'll again go to the start of the while loop, and now while checking, you'll say while I not equal to 0. But now I has become 0. So this statement becomes false, and since there is an and in between, we don't care whether this statement is true or false. If the first statement is false, the entire composite condition becomes false and you'll exit outside the while loop, which means that the decrease key function is done. So remember, delete key had called decrease key. So after decrease key is done, what we are left out with, we've brought this value that we wanted to delete. We wanted to delete 40, right? So we passed the index 3, which had the value 40. So now basically we converted 40 to minus 1, that is a very small integer value, and we have brought it to the root level. So decrease key operation is done. So first part of the delete key function is done. Now after decrease key comes back to the calling function, which is delete key, step 2 will start its execution. And step 2 is saying extract min. So remember, extract min was doing nothing but deleting the root node, or basically completely returning this and eliminating it. So let's quickly go to the steps of extract min, and I'll rush through them because we've already seen that in previous tutorials. So don't want to drag that too much. Okay, so this is the extract min pseudocode. Let's go step by step quickly. So first step, we check if heap size, which is 9 right now, is it less than equal to 0? No, heap is not less than equal to 0, it is 9. Second step is heap size 1. No, heap size is 9. So first two steps will not be executed. We'll go to step 3. We'll say root equals to h array of 0. So root equals to h array of 0. We've made it minus 1. So root is going to have minus 1. Then we will say h array of 0 equals to h array of heap size minus 1. Heap size, as I said, is 9. So 9 minus 1 is 8. So h array of 8 is 75. You can see that is the last value. So 75 will now be copied at index position 0. So let's do that. So 75 is now copied over here. Then we say heap size minus minus. So heap size becomes 8. So after that we say min heapify. And now again, when you copy 75 at index position 0, this breaks the principle of min heap, right? Because at the root level we want the smallest value. But right now you can see 75 is not the smallest value. So that's why we have to recreate the heap starting from the top to bottom. So let's see the min heapify function quickly. So extract min will now call min heapify. So basically delete key called extract min. Extract min is calling min heapify now. So I hope you get the flow of the different function calls. Okay, so from the extract min we've called heapify. This is the heapify code and we've passed 0, right? So now we create L equals to left of I. Let's write L over here. Who's the left of 0? It is 1. So L will become 1. We'll get index position 1. Then at step 2 we are saying R equals to right of I. We'll get index position 2. I hope you know the left and right functions are again user defined functions. They are simple formulas to give the left and right child index positions. Then at step 3 we say smallest equals to I. I is nothing but 0. Let me write I equals to 0 over here. So smallest will get the index position 0. Now we check if L is less than heap size. L is 1. Heap size is 8. Is 1 less than 8? Yes. And h array of L is less than h array of I. L is again 1. So h array of 1 is 6. Correct? Is 6 less than h array of I? I is 0. So h array of 0 is gonna be 75. Is 6 less than 75? Yes. So first two conditions are true. Then we say smallest equals to index position L. L is 1. So now 1 is going to be transferred in the smallest variable. So smallest will become 1. So out of these two, the smallest is index position 1. So we've calculated this as of now. So we compared these two nodes first. Now we will compare 6 and 21 in the next step. So at step 5 we say if R is less than heap size, R is 2 less than 8, yes. So first condition is true. And H array of R is 2, so H array of 2 is going to be 21. Is 21 less than H array of smallest? Smallest is 1, so H array of 1 is 6. Is 21 less than 6? No. So this condition becomes false, hence this if will not be executed. We will go to step 6. In step 6 we are going to say if smallest is not equal to I. Smallest is 1 and I is 0. 1 is not equal to 0. So this condition becomes true. In that case we are saying swap H array of I is 0. So H array of I means 75. So we are swapping 75 with H array of smallest. Smallest is 1. So H array of 1 means this index position. So these two nodes are now going to be swapped. So let's do that. So 75 and 6 is going to be swapped. So 6 comes over here, 75 goes over here. 6 comes over here and 75 goes over here. Alright. After this, we again recursively call min heapify and we pass smallest, which is index position 1. Right. So smallest is 1. So we are passing this index. So again we will re-execute this min heapify in a recursive way. So let's recursively execute it. And this time we are passing 1. So now again these variables will be calculated. I, L, R and smallest. And this process will keep on going. So I will be now 1. Left of 1 is going to be 3. So L is going to be 3. R is going to be right of 1 is going to be 4. Correct? These are index positions basically. Smallest will again become I, which is index position 1. And now again the comparisons will be made between these 3 nodes and the smallest one will be swapped at the root of these 3 nodes. So over here smallest is 33. So 33 will come at 75 and 75 will come at 33's position. Correct? So let's quickly do that. I'm not explaining every step over here. You can dry run it yourself. So 33 comes over here and 75 goes over here. So in the array also 33 and 75 will be swapped. Okay. And again min heapify will be called on index position 3. Okay. And this time when you compare these 3 nodes, you will not compare it with this node because index position 8 is now not a valid entry or not a valid node because basically we have reduced the heap size to 8. So we only have index position 0 till 7 to play around with. So even though in the array we have 75 over here, it is not going to be a part of our heap structure. Okay. So now only comparison is going to happen between 75 and 81, and since 75 is smaller than 81, the swapping is not going to be needed. And then you have your final min heap data structure recreated using the min heapify recursive function. Okay. So now if you see, we have again a proper min heap which is following the min heap principle where for a particular node, its parent is going to be smaller than its own value. Right. And after the last min heapify call, you will come back, you will come outside the min heapify, you will come to the calling function which was one more min heapify, you will trace back the entire function call path, and ultimately you will come back to extract min. Extract min will also be completed, you will come back to delete key, and basically if you observe, we have successfully deleted what we wanted to delete initially, which was the number 40, which was at the index position 3. Right, it was over here, 40 was deleted, and in the array you cannot see 40 anymore, and you also have recreated the min heap. So this was the entire delete key operation, which is split into 2 parts. First part decreases that particular value that you want to delete to a minimum value and you bring it to the root node. The second part is you call extract min, so you extract the root node because that is where you've brought that minimum value, and then you recreate the min heap using the min heapify function, which is called inside the extract min function. Okay, so it's an indirect method, but that's how you do delete operation in heap data structure. And I hope you've understood the entire working. Let's quickly jump to the C++ program, that is the practical side, and see the implementation and working. Okay, so I've opened up our C++ program which we've been building throughout the previous tutorials of min heap implementation. If you don't have this, don't worry, I'm going to be sharing the entire code along with the theory on our official website. So you'll find the link to the article in the video description. You can make your own notes, you can copy the code and run it onto your side. I highly recommend that you type at least once. So scrolling down, at the bottom, this is where we will do the decrease key and delete key operations. So I'm gonna paste the code over here, and I'm not typing from the scratch because then it will simply waste your time. This is exactly what we have in the pseudocode as well. Okay, so delete key has two parts, decrease key and extract min, and this is where decrease key is. Okay, alright. So these are the two functions that we copied in our min heap class. This is the min heap class that we had created. Inside that we have created these member functions now, these two member functions. And coming down in the main function, the delete key option is option number 3. So going to case 3, you simply have to uncomment this. We had created this program initially only in previous tutorials. You can check that out. So this is a menu driven program. And now let's save this, go to execute, compile and run. Hopefully everything should work fine. Okay, we are having a little bit of error over here, and this is something related to the swapping. We're doing swapping using the pass by reference methodology and not pass by address. So that's why it was throwing us an error. Hopefully everything should work fine now. Okay, yes, everything is working perfectly fine. So now let's enter the size of the min heap. Size is 7. Min heap created. First let's insert some values. I'll insert 55. I'll insert 34. Remember 34 is smaller than 55, so there will be swapping that happens. So 34 will come at 55's location. If you want to just see that happening, option 7 is for printing the array. When I print the array, you can see 34 came at 55's position. Even though we inserted 55 first and 34 second, since 34 is smaller than 55, the min heap property is that smaller value is the parent, right? So 34 became the parent of 55. Again, let's insert more values. I'll insert 7. So now the heap is going to be 7, 55, 34. Because 7 is smaller than 34, so 7 and 34 got swapped, right? Let's add a few more values. I'll add 21. I'll add 28. Let's see the values what we have. We have 7, 21, 34, 55 and 28. So right now the array looks something like this. Let's say you want to delete 21, right? So what we have to do, we have to call the delete key operation, which is option 3. Now we will have to enter the index of the heap array to delete that particular value. So index of 21 should be 1 because index starts from 0. So I'll enter 1 and the delete is done. I should have showed a message over here that delete operation successful, but it should be done. Let's actually print all the values and see if we have 21 still existing in that or not. So option 7 is for printing. And there you go, you can see 21 does not exist in the heap array and the min heap is recreated again. So our code is working perfectly fine. We've successfully implemented the delete key in min heap. We saw the pseudocode, we dry run it step by step with the help of diagram. We understood what happens at every step. And we ultimately wrote a C++ program to complete the practicals and implementation side as well. Okay, so if you've watched this video so far, if you're over here and understood the entire video, please give this video a like. It takes a lot of time and effort to make these videos. Let me know in the comments how this video was. Do share it with your friends. Subscribe and turn on the notifications for further DSA tutorials because many more are coming soon and you'll get notified whenever I upload them. And thanks for watching guys. I'm gonna wrap up this video over here. See you in the next one. Peace.